Hello friends, so today we are going to solve questions from modern physics, and all these questions are from the year 2023, and today we are going to solve 9 questions, and all these 9 questions are from mains, and for the year 2023 this is part 4. So the first question, it states that consider the following radioactive decay process. The mass number and atomic number is 6 are given by. So decay process is given to us. From A it starts with a decaying of alpha, then it is beta minus, gamma, alpha, beta plus, final gamma, and the final product is A6, whose mass number and atomic number we are supposed to find out. Okay, so we can just stick to the given equation, and first of all there is loss of an alpha particle. So therefore we can say that from 84 we are going to get 82, and from 218 we will be left with 214. Okay, so 214 will be our mass number and 82 will be atomic number for our A1. And for our A2 we are having a beta negative, so A2 will be giving us 83 and its mass number will be same. Now then there is a gamma decay from A2 and A3, so our A3 will be giving us 83 of atomic number and mass number will be also same. Once again there is alpha, so from 83 we are going to get our 81 and it will be our 210. Then it is a beta positive, so beta positive is going to give us a 80 and our mass number will be same, and that is our 210. And finally we have a gamma, so gamma will be same, that is our 80 and 210. So therefore option number 3 will be correct. Next question, it states that the energy released per fission of a nucleus 240x is 200 mega electron volt. The energy released if all the atoms in 120 gram of pure 240x undergoes fission is dash into 10 to the power 25 mega electron volt. So we have to find out its value. So we are given that the full decay or full fission should be consisting of 120 gram, and the mass number is given to us, and per fission as well as the Avogadro's number is also mentioned to be over 6 into 10 to the power 23. So first of all we are going to find out the number of moles, and before that let's write that the mass of the element is given as 120 gram and its mass number is 240 from here we can find out the number of moles. So we can say number of moles will be equal to mass divided by the molar mass. Mass given to us is 120 and molar mass is 240. This gives us 0.5 moles. And from this moles we can easily find out the total number of atoms. So we can say number of atoms moles are 0.5 and it is 6 into 10 to the power 23. This comes as 3 into 10 to the power 23 atoms. And it is given that energy released per fission is 200 mega electron volt. Okay, so basically means energy per atom is 200 mega electron volt. Therefore we can say that energy per atom is equal to 200 mega electron volt. So total energy we call this as E. E will be equal to total number of atoms, that is 3 into 10 to the power 23, and energy per atom is 200 mega electron volt. So multiply by 200. Therefore we get our E will be equal to 6 into 10 to the power 25 mega electron volt. And we are asked for that it is dash 10 to the power 25 mega electron volt, which gives us that the answer will be 6. So this comes as 6 10 to the power 25 mega electron volt. Next question. It states that the ratio of density of oxygen nucleus and the helium nucleus is. So we have to find out the density. A basic formula for the density we already know. We know that our density, suppose that is rho, is equal to mass oblique volume, or we can say A and proportionality for R cube, where is the A is the mass number. Okay. So this A is our mass number and R is the radius of the nucleus. Radius of the nucleus. And we already know that our radius of nucleus, that is R, in terms of our mass number, we also know. Okay. So we can say our radius of nucleus, that is R, is equal to R naught A raised to power 1 by 3. Or from here we can say that our R cube is proportional to A. So therefore we can say our density, that is our rho, our A is our, it is proportional, A is our R cube and the denominator is already R cube. Therefore from here we can say that our density is constant. Okay. Or in simpler terms we can say, in both terms I can also write this as rho is proportional to A upon A. So this will be also giving me it is constant. So basically means it is independent of R as well as A. So you can say independent of R and A. Therefore ratio, and ratio is for oxygen to helium. So you can say density of oxygen, density of helium will be giving us a ratio 1:1. Therefore option 3 is correct. Next question. It states that if a radioactive element having half-life of 30 minutes is undergoing beta decay, the fraction of radioactive element remains undecayed after 90 minutes will be. So in this case we are given the half-life. So we can say half-life is given to us, that is our T half is equal to our 30 minutes and time elapsed is our 90 minutes. Time elapsed, that is our small t, is our 90 minutes. Okay. And decay is said to be beta decay. Decay is our beta decay. And okay, first of all let's solve the question, then we can discuss the important part with respect to this beta decay. So we can find out that number of half-lives elapsed during this 90 minutes. Number of half-life elapsed, that is our n, will be equal to time elapsed and divided by the half-life, which gives us 90 divided by 30 giving us 3. So it means there will be total 3 half-lives for this 90 minutes. And from here we can find out the fraction remaining undecayed. Here we can say undecayed fraction. Undecayed fraction remaining, that will be equal to 1 by 2 raised to power n, which is 1 by 2 raised to power 3, giving us 1 by 8. So option number 1 is correct. Option 1 is correct. So in this case, if we see the solution, what type of decay that is taking process does not matter. Okay, it is simply decay, whether it is beta decay, gamma decay or alpha decay, that doesn't matter, because the fraction, undecayed fraction, is only depending upon the number of the half-life that has been elapsed, or basically you can say time half-life as well as time elapsed. So we can say that decay mode does not affect fraction undecayed. So we have to remember this part, that our decay mode does not affect fraction undecayed. Next question. It states that a radioactive element 242X92 emits 2 alpha particles, 1 electron and 2 positrons. The product nucleus is represented by 234YP. The value of P is. In this case, we are having a parent nucleus is given to us and we have a daughter nucleus, and in between there are decay of 2 alpha particle, 1 electron and 2 positron. So you can say that our parent nucleus it is given to us as 242, 92, and this is going to emit 2 alpha particle, 1 electron and 2 positrons. And 1 electron is sometimes also written as our beta negative, and this positron is also written as beta positive. And the daughter it is said to be YP and 234, and we are supposed to find out this value of P. So we are having 2 alpha particle, and so let us find out what will be the effect on the mass number as well as the atomic number for the respective decay. So we start with the particle, and we have change in A and we have change in Z. So first particle is of alpha, and alpha is our, we can write this as alpha as 2, 4. So there will be decrease of 4 per alpha. Decrease of 4 per alpha, and change in Z will be decrease by, you can say decrease by, here also let me put by, not of, decrease by 2 per alpha. Second one is our electron. We can write this as our E negative, or we can just beta negative. So there is no change in our A, so A is our no change, and Z is increased by 1. And finally we have a positron, which is our beta positive. So beta positive also there is a no change, and there is a decrease by 1. So we are having 2 alpha particles, so therefore there will be a total of 2 into 4, that is decrease in 8, and this will be also 2 into 2 decrease by 4. And in this case rest are our single terms, so that doesn't matter. So let us first of all find out our mass number. Starting mass number was our 242, and there is a decrease in 8 only, rest there is no change, so this will be minus of 8, 234. And then we can calculate our atomic number, that is Z. This is our A, and we have our atomic number, and atomic number is decreased by 4. This is an increase, and this is also decrease. So initially was our 92, so we have 92 minus 4, we have increase by 1, then decrease by 1. So this will be giving us 1 and 1 automatically cancels out, and one second, there are 2 positrons, my mistake. So there are 2 positrons, so this is decreased by 2. So increase by 1, decrease by 2. So this comes as our 93 minus 6, giving us 87. This is our Z, or we can say this is our P. Therefore value of P is our 87. So value of P is 87. Next question. It states that substance A has atomic mass number 16 and half-life of 1 day. Another substance B has atomic mass 32 and half-life of half day. Both A and B simultaneously undergo radioactivity at the same time with initial mass of 320 gram each. How many total atoms of A and B combined would be left after 2 days? So we are given that we have 2 substances A and B. So we have our substance, that is our A, and we are having substance B, and their atomic mass number A is given as 16, B is given as 32, and their half-life, that is our T half, it is given as 1 day, and for this it is given as half day, and initial mass for both is given as 320 gram. Okay. So after 2 days we have to find out what will be the total atoms combined. Okay. So from first of all we need to find out the number of moles for A and B. So we can say that number of moles for A, or let's write the formula first of all, that is N is equal to, we have this as mass and we have the molar mass. Or we can say mass is, let us suppose, our m0 and molar mass is our mass number, atomic mass number that is given to us. It is also represented as A, and this is our m0. Therefore, for A, we can write this as Na will be equal to m0 is given as 320 and it is 16. So from here we get 20 moles, and for B, that is of Nb, we have 320 and multiplied with 32, this giving us 10 moles. And now we can find out the number of half-lives elapsed for each, because the finally number of days total time, that is our T. Our time elapsed is T. So you can say that number of half-lives elapsed for, let us solve it for A, and for A we are given this, the formula is our T upon T half. So T is given as 1 day and T half is our, sorry, T is given as 2. T half is given 1. So from here give it 2. And for B, and this is our 1 by 2 giving us 4. Now we can easily find out the fraction remaining. Fraction remaining, and the formula is our 1 upon 2 raised power, let us write this as capital N, because here this usually it is written as small n, but in order to avoid confusion, this is a capital N, so this will be capital N A and capital N B. Therefore, for A, we are going to get this as, let us call this as F. So Fa will be equal to 1/2 raised power Na, which gives us 1/2 raised power 2, which will be 1 by 4. And for B, that is Fp is equal to 1/2 raised power Nb, which is half raised power 4, giving us 1 upon 16. And in this case, okay, we have to find out the total number of atoms. Okay. So the remaining moles and we start with our A. So we can say for A, let us call this as our Na prime will be equal to 20 was our starting and it is 1 by 4, giving us 5 moles. And for B, let us call this as Nb prime will be equal to 10 multiplied by 1 upon 16. This gives us 0.625 moles. And from these moles respectively, we are going to find out the number of atoms. Remaining number of atoms, and for A, let us call this as our Na prime will be equal to, moles are 5, Avogadro number 6 into 10 to the power 23. This gives us 3 into 10 to the power 24 atoms. And for B, let us call this as Nb prime will be equal to 0.625 multiplied by 6 into 10 to the power 23. This gives us 3.75 into 10 to the power 23 atoms. We have to find out the total. We simply add them. So total, let us call this as N total, will be equal to Na prime plus Nb prime. That is our 3 plus 3.75 into 10 to the power 'Okay, let me convert. This will be becoming as 0.375 into 10 to the power 24. So therefore we can write this as 0.375. 0.375 10 to the power 24. This gives us 3.375 into 10 to the power 24 atoms. Next question. This is basically assertion and reasoning based question. So assertion states that the nuclear density of nuclides, your B, lithium, ferrous, neon and Bi, I don't know what is this Bi anyways, can be arranged in this way, and the radius r of nucleus is related to its mass number, where r0 is a constant. So we have to choose which of them is the correct answer. Okay. First of all, there is no relationship between these two. Okay, so at least we can just, this is correct or not correct, this will be both wrong. So we have to check which of C and D will be the correct option. And in order to Anyways, this standard formula we already know. If you want, we can just drive it also. And because we are interested in, okay, let me find out first of all the density also. Okay, that will be helping in the final whether A is true or not. And this is a standard formula also, so obviously R is our true, but we have to check whether A is true or not. Only option left, no problem. So we are interested in finding our density. So density we know is our mass oblique volume, and we can write this as our A multiplied by MP, and volume is our 4/3 pi r cube, or r naught rather. R naught is our standard radius, and multiply by A, and this gives us our MP, and we have this as 4/3 pi r naught cube. Therefore, from this we can say the density is independent of mass number. Is independent of the mass number. Therefore, this relationship does not hold true because the density is independent of the mass number. Okay. And secondly, obviously this is standard relationship, so this will be true. So only option our R is true, whereas A is false. So option C is correct. Next question. It states that a radioactive nucleus decays by two different processes. The half-life of first process is 5 minutes and that of second process is 30 seconds. The effective half-life of the nucleus is calculated to be alpha upon 11 seconds. The value of alpha is. So we are given that there are two independent processes. So let us state that for the first process half-life is 5 minutes. So we say half-life of first process, that is of T1, it is given as 5 minutes, or we can say as 300 seconds. And we have half-life of second process, let us call this our T2, that is our 30 seconds. So we are going to find out the effective half-life, and in order to find out effective half-life we are going to make use of the decay constant. And we know that the effective decay constant, and please remember this formula is only applicable if there are independent decays, means T1 is not dependent upon T2. Okay, in that case we are going to use this particular formula. Okay, so we can say that for multiple decay processes and we have to remember these are independent decay. Independent decays. The effective decay constant let us call that as a lambda effective, then this will be equal to decay constant for the first process plus decay constant for the second process. In this case there are only two processes, so only two decay constant. And we already know that our lambda is equal to natural log of 2, and this is our t half. So from here we can write that our lambda 1 will be equal to natural log of 2. First half life we called as t1, and second is our lambda 2. Second half life we called as t2. Therefore lambda effective will be equal to natural log of 2 t1 plus natural log of 2 divided by t2. And one formula we can also write that our lambda effective will be equal to natural log of 2, and this we can call as a t effective. And we need to find out our t effective. Therefore from here we can say that our t effective will be equal to natural log of 2 divided by lambda effective. Therefore we can say that our t effective will be equal to natural log of 2, and we can take natural log of 2 as common. We get this as 1 upon t1 plus 1 upon t2. This natural log cancels out, and we can substitute the values. This becomes 1 upon and let me take the LCM. This will be t1 t2 t1 plus t2. So t1 was our 330, so this comes as 300 multiplied by 30 divided by 300 plus 30. So we get our T effective will be equal to, this will be 9, and we are going to have here 9000, and this will be our 330, and 0 we can easily cancel out, and we can, this goes by 11 and this goes by 300. Therefore we get T effective will be equal to 300 by 11 seconds, and I think that is given as alpha by 11. So we can say this is given as alpha by 11. Therefore we can say value of alpha is equal to 300. So value of alpha is 300. Next question. It states that a free neutron decays into a proton but a free proton does not decay into neutron. This is because. Okay. And this is basically based on the conservation of energy. And first of all, it says that neutrons decays into proton. Therefore, we can write it in the form of equation. We can say our neutron is going to decay into a proton and plus our electron negative. Okay, and there will be also our anti-neutrino part there. Okay, and this is possible only because of the conservation of energy. So we can say this decay is energetically allowed. Because mass of neutron is slightly greater than our mass of neutron is slightly greater than the combined mass of proton and then we have electron and anti-neutrino. Therefore, we can also say that the mass of left hand side is slightly greater than mass of our proton plus mass of our proton by mass of our electron plus mass of our anti-neutrino. Whereas the free proton cannot, you can say decay, word is decay, because this condition will not hold true. So we can say mass of proton is less than mass of our neutron. So therefore, decay would violate conservation of energy. Therefore, the correct option is that our neutron has a larger rest mass than a proton. So option 4 is correct. So this completes the part 4 for the year 2023. In this part 4 we solved 9 questions from the mains only. So this completes the part 4 for the year 2023 consisting of 9 questions. Thank you.